Hey, howdy folks, how we doing? Welcome back. All right, so we are getting this idea of doing related rates, and we've already done quite a few of them so far, right? We did 5 last night, and then today in class, we did more. We did 3 more. So we can do 5 more tonight, and then we'll do 2 more in class. So by the time we're done, we've done 15 together, plus you're gonna have all your classwork you're doing. So just so as a quick reminder, we remember how we said there's 3 different things, or 2 different things we're always asking ourselves. First thing is, what do we know that is not changing? Or in other words, what is constant? What do we know that's not changing that is constant? Yeah, we're always looking for that. What's not changing? What's a constant value or a constant rate? And then the other thing we said we're trying to always find is, what are we trying to find? And when are we trying to find it? In other words, we called this the little snapshot in time. When is this taking place? Because if we can figure out when it's taking place, and we've got a pretty good shot of being able to determine the exact value. Why did I use purple? I wanted black there. There you go. There we are. All right, so we're going to go through a few of these together. So the first thing I'm going to have you guys do is take a look at this shape right here. All right, walk through this and figure out what you know. Go ahead and pause the video, and then we'll come back and talk. All righty, well, let's see here. The first thing I see is a trough. And for some of you guys, maybe you're not quite familiar with what a trough is, but the trough has equilateral triangles. The trough is nothing more than just a feeding bin. Equilateral triangles means the edges of it are all the same. So that means this side is congruent to that side, is congruent to that side. So we're going to have some sort of a trough here. So let's see if I can't draw a real quick trough so you can get an idea of what it looks like. Again, remember, if you're going to be a math teacher, you got to become a professional shape drawer. I'm not necessarily the greatest at it, but it is what it is. There we are. All right, well, that at least gives you an idea of what we're looking at here, right? So, first thing we were told is that the trough is 12 feet long. If you notice, that's a constant value. It's never changing. The length or the depth of this is never going to change, okay? For instance, another way to look at it, if I were to stand this up on the side, maybe it will help you kind of see it a little bit better here. Or just part of my chicken scratch there. You can tell how maybe I was a little bit better with the straight lines there, but you can kind of see it now maybe a little bit upside down like that, right? So what we have here is that's where the 12 would be. So that 12, that's the height of this prism. So I'm going to go ahead and let that be my h value. That's a constant value. It's never changing. Now, let's not call it h. Let's call it, because I see a triangle here, let's let the h be the height of the triangle. So we'll call this thing, maybe we'll call it d for depth. That'd be a good thing to call it. That's never changing. That's 12 feet. All right, so let's figure out what else we're dealing with here. It says that the sides are 2 feet long. So, okay, well, that means that base of this triangle here is 2 feet long. I'm going to draw it down here. Would be good to know what the height of that triangle is, because remember, the area of a triangle is base times height divided by 2. So let's think about 30, 60, 90 triangles here as well. It'd be nice to know what that actual height would be. So if we're looking at the whole thing here, and this thing would be, we'll call this x for the side length. All right, so if I draw a straight line all the way down here, we saw back in integrated 2 that makes a 30, 60, 90 right triangle. Like that. So if the whole thing is x, and that means this whole thing is x, if we split it in half, that makes this side right here, we said that was x divided by 2. And we said that makes this one x divided root 3 divided by 2. Now, majority of the time, the College Board will give you guys geometric relationships, but special right triangles is one they would actually want you to remember. So in this case, our x value is 2 because we have a side length of 2. So if I plug 2 into this, 2 divided by 2 would be 1, root 3. That means the height of my triangle here is root 3. All right. Well, let's go ahead and get rid of that. Then we have that down. We know what the triangle is going to kind of look like. So at least we know what the relationship is here. And let's see what else we got here. What else do they tell us? Sides 2 feet. It says water is being pumped into the trough at a rate of 3 cubic feet per minute. All right, so we got water being pumped into our trough at 3 cubic feet per minute. And again, looking for those key words. And if I see cubic, you know what I'm thinking of, friends. I'm thinking of volume, right? Volume. So we're dealing with volume here. So this rate they gave me, well, that's the rate for volume. So that would be 3 cubic feet per minute. So what we need to do then is we need to figure out, well, what's the height, or what is going to be the actual idea, the volume for this shape. So in order to figure out that, so if, well, we'll come back to that actually. Let's first figure out what else we know here. We're going to be asked to figure out the rate the water is rising. Okay, so we're going to be asked to find the water. So that's this height of the triangle that we're actually figuring out here. Okay, so that's what we're looking for. We're going to try to find dH dt, the height of the triangle. So, and we're going to try to figure it out. Remember, they always got to give us another value. In this case, that other value they gave us was when the height, depth, or the height of the water, looks like I forgot an H there, is 1/2 foot. All right. Well, it would have been good if I would have remembered an H there. Why don't you guys just go and add one in there? Woo, there we are. So when depth of the water is 1 feet. So when the height is 1/2 foot. All right, so let's take a look at this volume. Now, the hard part is here is as this rate goes up, as the water level goes up, it's going to form other triangles along the way, right? And these triangles, like we saw on the cone, they're going to be essentially the same type of relationships, the same similar relationship to our big triangle. So the base and the height, they'll still be the same. So I do know that that our volume is always going to be sum base times height divided by 2. So that's the area of my triangle, and then times the height of the prism, or the depth of the prism. So that 12. And we said that 12 is not changing. So I'm technically dealing with 6 base times height. So that'd be my volume. However, if you notice here, if we're looking at this right here, all I want is everything in terms of the height. I don't want the base. So we can use that similar triangle again to help us out. So if I take my big triangle right there, we have our side length that was 2. And then we had our height that was root 3. And as water is getting poured into this, I'm going to have multiple side lengths. Yeah, let's call that B for base. And height. So by making ourselves a little special right triangle here, or similar triangles here, I can have 2 over the base. equals root 3 over the height. And again, this gets back to that idea. We don't know what we don't know until we find out we don't know it. So if I cross multiply it, I get 2h equals root 3 times b. And again, we're wanting to deal with h. So I want to get b by itself. So 2h over root 3. Two h over root 3 equals b. So that means every single one of my bases is going to be 2 root 3 over my base. So if I plug that in here, let's come back here then. If I plug that into my base over here, so that'd be 2h over root 3. And that would be then times h. Or in other words, I could say my volume, if I clean all that up, it's ugly. It looks like I have 12 over root 3. H squared. So now we have ourselves volume. So I'm going to go erase some of this stuff here so we can kind of clean it up here. So saw what the shape of this looks like. And this is a weird shape. All right. And we got that. We use our similar triangles there. That's good stuff. I think now we're actually ready to go ahead and solve the problem. So let's take a look-see. Volume. 12 over root 3 times h squared. So we're going to go ahead and do our dv dt. Equals 12 root 3 times 2h dh dt. Now we can go ahead and pull this all together. And again, this is one of the tougher ones we'll have to deal with, or that we'll see. I just wanted to kind of good way to start us off here a little bit, kind of make sure we're thinking here tonight. So the height would be dv dt divided by, holy wow, what is that? 24 root 3h. All right, let's plug in our value. So this was when h was 1/2. And again, we're keeping that good notation all the way through. So dv dt, well, that was, what was that? That was 3. All right, let's go ahead and throw that up there in the top. And what else do we know here? We have our 24 over root 3. Times our h, and that h would be times, 1/2. And like I have told you guys so many times, I am not simplifying anything if this is the free response portion of the test. I will leave it alone. You need to leave it alone as well. But again, if it's multiple choice, or because some of you just can't seem to leave it alone, if you were to clean this whole thing up, you would end up with root 3 over 4. Root 3 over 4 feet per minute. Or if you were to do the approximate, and again, you should be telling yourselves, if we do an approximate, We're always going out to 4 decimal points, at least 4 decimal points. So 0.43301. I went to 5 that time. Oh well. Hey, you win some, you lose some, huh? All right. Here we go. Well, friends, it is time for us to have a little fun. Just going through and trying a few of these. So we're going to go a little quicker than we did last time. Go for it here. At this point in time, let's see how y'all do. Set and go. Pause the video and try it. All right, you unpaused it just in time to watch me erase. I feel like every time I bring this thing out, I feel like I'm a lightsaber, using a lightsaber there. I'm telling you, these are the simple pleasures, friends. The simple pleasures. All righty. Here we go. Rope is attached to the bow of a sailboat. Assume that the rope is drawn in over a pulley that is 5 feet higher than the bow. All right, so I'm going to draw a real quick picture here. No making fun of the picture. All right, I got a boat. Woohoo. Call that the SS Wildcat right there. All right, and now this is being drawn in. To a pulley. And we were told that the height of this boat is 5 feet above. 5 feet above the boat. So I believe that is then going to be, I'm going to call that Y since it's a vertical distance. That would be a constant value. That's never going to change. That pulley cannot move. The rope can move, the boat can move, but pretty sure that 5, that where that pulley is, it is going to be stopped. All right, so we got R and we got X. Let's keep going, friends. All right, next thing. The bow, the rope is being drawn at a rate of 2 feet per second. So this is the rope. The rope is being brought in. Now think about this. Is the rope getting longer or shorter? And I'm sure you guys figured that out when you did this. It's getting shorter. So that makes that a negative 2 feet, not a positive, negative 2 feet per second. It says determine the rate the boat is docking. Okay, so the rate the boat is docking. So think about the boat. That's going to be that X value. So as the boat gets closer to the dock, it's the X value that gets shorter. We're going to try to find this when what? When the rope from the bow to the pulley, it's 13 feet. So we're going to try to deal with this when the rope is 13 feet. And friends, the astute math students you are, I know that you're looking at this shape right now. You see that triangle and you're thinking to yourselves, aha, Williams, I got this. That would be the Pythagorean theorem, and you'd be right. So x squared plus 5 squared, or 25, equals r squared. All right, so friends, why don't you take a second and go ahead and take the derivative if you haven't done it yet and solve it. All righty. You unpause the video, so I'm assuming you solved it, or you just wanted to see me do it. Either or. Here we go. So we're going to take our derivatives, 2x dx dt plus 0. I love constant numbers. And we have 2r dr dt. And we've seen something like this before. We don't know every value because we don't know x. So we're going to take a quick time out here and figure out what x is. At this snapshot in time, when r is 13, we know the height is 5. We got to figure out what x is. So if you realize that this is a Pythagorean theorem or a Pythagorean triple, awesome. You've already figured out the value. If not, don't worry about it. You can figure it out for yourself. And when you do that, you're going to find out that x is 12. So we can go ahead and add that up here, and x is 12. So we're going to add that to our little snapshot in time. So I'm going to divide out the 2's. They're gone. I'm going to get dx dt by itself. And when I get it by itself, I'm left with r times dr dt divided by the x. So again, just so we see it here, I saw that they both had a 2 on both sides, so I just canceled them out. So now it's big plug and chug. So we're going to find dx dt when r is 13 and when x is 12. So big giant plug and chug. Here we go. R, well, we said that was 13. dr dt, well, we already found that one earlier. That was -2. And x, well, we found that one as well, and that was 12. So friends, you know what I'm going to say now. You're done. Don't go any further. Stop when you get here. It's on the free response portion of the test. Stop. But if not, you want to clean it up. All right, that's -13/6 feet per second. And it makes sense that it's negative because the distance from the boat to the dock is getting shorter. Or if you wanted to use decimals, I don't know why, but we can. All righty, 2 down, friends, 2 down. We are cruising now. 2 down, 3 to go. Here we go. There's a different one for you. All right, why don't you pause the video, or you can try it. The setup while I am erasing, and then we'll try it. All right, here we go. We're shooting rockets into the air. That's kind of fun. The rocket is 2 kilometers high. Now, friends, think about a rocket for a second. If a rocket is 2 kilometers high, this is not a constant value. Because our rocket here as it's going in the air, it's going up, right? So this is not a constant value. So I already know that this, I'll come back to this 2 kilometers high. I know that that is not going to be what I'm looking for here, right? All right, so let's see if we can't play with this here. It is moving vertically. Upward at a speed or a rate of 300 kilometers per hour. Well, not the fastest rocket in the world, I guess. So that means I don't know why I put h there. Oh, I'm going to change that to y. So that means that vertical rate, that's going to be a constant value. So let's go and put that in here. dy dt equals 300 kilometers per hour. What else we know? At that instant, what is the rate of the angle of elevation? Whoa, wait a second. Dealing with angles now? All right, well, so let's make an angle. Angle of elevation to my rocket. All right, so I'm going to call that thing, I'm going to call it, let's go and call it theta. Now, friends, we're not going to go through and ever actually figure out this angle, but that doesn't mean we can't figure out the rate that it's changing. Okay, so don't think, oh, we're going to have to go back and change what mode does our calculator need to be in and all those kind of things. We're not going to play with it like that. So we're going to be able to figure out a different way. And what do we know here? There's got to be something else here. As seen by an observer on the ground, 5 kilometers from the launching pad. Well, friends, that value right there, that looks like a constant value because my person standing 5 kilometers away, that person's never moving. That is a constant value. So that means that this right here, so that's where that initial value came in, that 2 kilometers high. So that we're going to be trying to figure out that rate of change when y is 2. So all of a sudden, I'm going to have to start dealing with something that deals with this theta. So now I'm going to be thinking over here. In regards to my y, this would be the opposite side. Since I'm dealing with an angle, I have to go and back and deal with right triangles here. That's my adjacent side. So opposite and adjacent, friends, that's going to be tangent. And that means that this tangent is opposite over adjacent. So put another way, my equation here is tangent. That equation, that relationship will not change. And I'm going to, instead of doing y over 5, I'm going to change that to 1/5 y. I just think that'll help me out a little bit. I don't like using the same color things. I'm going to change that as well. There. Why? Because I can. I control the mouse. I can change it to whatever I want it to be. You control the mouse, you could change the color as well. All right, so that now I know what trig function I'm going to be dealing with here. Well, friends, that's my constant function that I'm going to be taking my derivative of. So why don't you guys do me a favor? See if you can solve it from there. Go for it. Just pause the video and go for it. Of course, you probably should put an equal sign there. All right, now pause the video. All right, we're back. I'm sure you all paused the video. So tangent squared, that'd be the same thing as secant squared. Oh my goodness, secant squared. Oh, we'll come back to that here in a second because that presents a whole nother problem. And I have 1/5 dy dt. So now let's think about secant for a second. Secant is hypotenuse over adjacent. It's the reciprocal of cosine. Friends, I don't have my hypotenuse. So again, we're looking at something I didn't know that I needed to know until I found out I didn't know it. So I know that my value here is 5, and I'm dealing with my snapshot when y is 2. I got to find out what my hypotenuse is. So 2 squared plus 5 squared equals c squared. And if we go through and clean this up, I mean, c is going to be the square root of 29. So I have another value that I didn't know, I needed to know. And this is why I said you don't need to actually use any inverse trig or anything to figure out those angles. We don't need that. We're just going to use these values that are given to us, or this one that we found. All right, so we come back here. D theta dt. That's going to be 1/5 dy dt. All over secant squared theta. And by the way, friends, if I have secant squared in the denominator, I bet I can move that up real quick and make that cosine. So cosine squared theta. All right, let's plug in some values, friends. Here we go. All right, so we're plugging it in when what? When y is 2. And when c is root 29. Those are a snapshot little things there. So I'm going to have my 1/5 times dy dt. What was dy dt again? That's right, that was 300. We haven't dealt with that number for a bit. Times cosine squared theta. All right. So cosine squared theta. So I'm going to be squaring cosine. Cosine is adjacent over the hypotenuse. So what was my adjacent value? Well, that was 5. Forget, here's our theta right here. So adjacent was 5 over, the hypotenuse. Well, we found the c value to be root 29. And friends, I'm pretty sure by now you know what I'm going to tell you. We are not going any further. There's no reason to, but you may ask what one we're using. Well, always radians. So this is radians per hour. And for my friends that wanted to go further because, well, they just can't help themselves, that would be 1,500 over 29. Radians per hour. Or that would be about, and I'm not going to be able to put the radians per hour at the end of this one because I am just plain flat out running out of room. 51.7241 radians per hour. All right. Oh, 3 down, 2 to go. And like we said, this just takes practice. Again, takes practice, 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 because we're doing the same pattern over and over and over again, aren't we? All right, go for it. Pause the video and try it while I erase this. Hey, it's our old friend, the conical paper cup. Amazing how, for whatever reason, that shape is used a lot. So we'll bring our conical paper cup back. All right, what do they tell us? The height increases. Oh, that's fun. We're dealing with height this time. The height increases at a constant rate of 1 inch per second. All right, well, that's constant. So we'll bring that back here, dHdt. Equals 1 inch per second. I like 1 inch. I can multiply by 1 inch real quick. 1 inch per second. Yep. What else we got? If the cup is 8 inches tall. All right, so we have some dimensions of our cup here. The cup is 8 inches tall. That'd be an awfully big snow cone right there, friends. 8 inches tall, and it has a diameter of 4 inches. And by the way, if it has a diameter of 4 inches, that means it has a radius of 2 inches. I don't really care too much about the diameter. It says, what are we trying to figure out here, friends? Determine the rate of the volume of water. All right, so we're going to try to find dV dt. When the height is 3 inches. All right, so when the height is 3, so when h equals 3 inches, I can do that. All right, and we've already saw before, notice our rate is dealing with height, and we're dealing with height here, so that means when I'm dealing with my volume equation, I'm only going to be dealing with height. So those that don't remember, here was our formula for volume, 1/3 pi r squared h. And again, just like we said before, the College Board will give you those geometric formulas. I just want to test your geometry because you'll need it for the SATs and some of that kind of stuff. They'll give you some of those formulas, but some of those you are going to be expected to remember. All right, so let's go back here and let's see if we can't remember how this whole thing plays out. Remember that was a very sloppy right triangle. So my height of this right triangle is 2 and 8, and we said, hey, we could have any right triangle in there. Remember doing that for a little bit? It's always going to be some r and some h. So we can figure out how to get rid of r by using our similar triangles again. 2 and 8. R and H. So 2 over 8, 2 over R, doesn't really matter. 8 over H. Cross multiply, we end up with 2H equals R, 8 times R. I don't know why I put the R first. All right, and we're trying to get rid of the radius again, right? So we're going to get the R by itself. And if we do that, we find out that R is 1/4 H. So the radius is always 1/4 the height, which means we're going to change our volume formula here. So instead of R, we'll plug in 1/4. And the volume formula that we want to use, friends, is pi. So 1/4 squared is 1/16 times 3 is 1/48, or 1/3, that is. So 1/48 pi, got an H in there, H cubed. So that's going to be our volume formula in there. So let's bring it over here. Pi H cubed. All righty, it's derivative time, friends. dv dt equals 1/48 pi times 3h squared dh dt and we could plug it in at this point in time. So let's do that. dv dt and we're going to plug it in when our height is 3. And I can already hear what you guys are saying. You're yelling at the screen now. I'm sure of it. Don't simplify. Good. On the free response portion of the AP test, do not simplify. So our H value was 3. And our, what was that? Our DH dt, go back and take, oh, I love that. DH dt, that was 1. That is right up my alley. Perfect. All righty. And we can go ahead and plug that in there. Now, notice this is a rate as a volume, so we are going to leave it in, why did I put feet? That should be inches. Still should have been inches. Inches, don't forget the cube, per second. All right, and if you clean this up, friends, if you clean it up, you are going to end up with, I kid you not, 9 pi over 16. 9 pi over 16 inches cubed. Or if you did the decimal, again, don't forget that approximate symbol, 1.7671. Friends, brings us to our final one. Whoopsies. Didn't mean to erase that. There we are. Our final one. All righty, here we go. And then, like I said, we'll do 2 more tomorrow in class. We will walk through 15 of these together. 15. Again, they just take a lot of practice repeatedly over and over again. All right. I'm going to pause the video and take a try at it. All righty, last one. Here we go. What do we know? We are traveling east from San Francisco towards St. Louis. All righty. East from, just about dead. It's saying, hey, plug me in. There we go. Whoop. Got to plug it in. That's always bad. All right, so we're going to be traveling east from San Francisco to St. Louis. And they said, and since that is a horizontal distance, I'll just go ahead and call it X. And they said your rate is 500 miles an hour. So I went east, and that rate is 500 miles per hour. So that's a constant rate. So let's make that the rate of X. So that's 500 miles an hour. And then we have another plane that's traveling north. Okay, well, traveling north from New Orleans to St. Louis. All right, we'll go ahead and call that one Y then. But more importantly, it's traveling at 600 miles an hour. All right. And by the way, in case you see it, let me go and draw it down in there. That's a right triangle, looks like we're making here, friends. Oopsies. All right. Don't know yet what's going on, but we'll figure it out. Find the rate of change. Rate of change of the distance. All right, well, that makes sense. Let's go ahead and call it D then. We're going to find dt when what? When the jets are 300 miles apart. So the jets, so if this is our first jet right here, our first jet, and our second jet was down here. So the distance between them, that would be the D value. So when the jets are 300 miles apart, that's that D value. So when D is 300 miles apart. And, oh, they told me something else. And, all right, and what else? And the whisper jet is 100 miles. Well, which one was the whisper jet again? That was the first one, right? All right, so that means when this one is 100 miles. So, whoopsie, that was a circle. When the whisper jet is 100 miles. So when X is 100 miles. Well, friends, I'm hoping at this point in time you're looking at this shape and going, I know exactly what shape that's going to be. I'm dealing with the Pythagorean theorem. So x squared plus y squared equals d squared. So 2x dx dt plus 2y dy dt equals 2d dt. And first though, I see that they all have a 2, so I'm just going to divide 2 out from everything. And I got to get the dt by itself. It's kind of fun to see. dt. Oh yeah, how's life so ring good? Got to get that by itself, so that's going to be equal to x dx dt plus y dy dt all over d. And of course, because it wouldn't be complete if there was something that we didn't know. And in this case, that thing we didn't know is the y value. So let's go find it. In our snapshot in time, this is not going to be drawn to scale. That's 100. That's 300. I have to figure out y. So 100 squared plus y squared equals 300 squared. And that means y is something big and ugly. And friends, that would be the number, well, I don't know. I never figured it out. Makes sense. 300 squared minus 100 squared. Works for me. By the way, if you do want to know what that number is, that would be about 282.8427125. The reason why I'm putting all those numbers there is if we're actually solving this problem, we don't round to our final answer. So if you are a person that likes decimals, make sure that you bring all those decimals with you. So 300 squared minus 100 squared. I didn't even bother to actually even figure that one out. Because, again, you're yelling at the screen right now, I don't like to simplify. All right, so we're going to plug in all these values, and friends, and we'll be able to call this a day. We're just about done. Let's just plug these in, and we will be done. So D is 300. X is going to be 100. And Y is going to be big ugly. Oh, you probably shouldn't call it big ugly. That's not nice. It is a number. I think the number is actually like 89,000 or square root of 89,000, but I don't want to deal with it. All right, here we go. Big ugly problem. X, what did we get for X? Looking around, oh, that was the 100. dx dt, what was dx dt? That was the 500. Plus, we have the y value, where it was y. Oh, that was that. Holy wow. All right, let's put that in there. 300 squared minus 100 squared. And then dy dt, that was the 600. We're just plugging in numbers left and right here, friends. And then the d value, well, that was the 300. And of course, I'm not simplifying, so that would be miles per hour, right? Perfect. But of course, some of you guys, I get it. I know you like to simplify. So that's about 732.3521 miles per hour. All right, friends. That brings us to the close tonight. But I'll see you in the morning. We'll do a couple more of these and just try to really firm up this idea of related rates. Again, we're just doing that same process over and over and over again. You guys will get it. You're doing great. Keep it up. Have a good night.